Hello everyone. In this video, we are going to discuss the Quicksort algorithm. So these are the contents of this video: introduction to Quicksort, implementation of Quicksort in C language, and some example of Quicksort. Before starting our discussion on Quicksort, let's know what is actually sorting. Sorting is the process of arranging the list of element in either ascending or descending order. Right? Okay. Simple. The next question is why sorting is required. Sorting is very important role. Due to sorting techniques, you can reduce the searching complexity. And if the searching complexity is reduced in your program or in problem, then definitely the complexity of the program will be also reduced. That's very important, sorting, because of to reduce the searching complexity. There are lots of reasons for the sorting, but these are the some reason for sorting, right? Okay. Now, due to this process, we are going to discuss with Quicksort, because he invented this, developed this Quicksort in 1959 and published a paper in 1961. His name is this person name is Charles Anthony Richard Hope. Right? This is a very fortunate person. He received the Turing Award in 1980. And for your kind information, you should remember this. Turing Award is the highest award in computer science field. Like Bharat Ratna is, it's the highest civilian award. Similarly, Turing Award is the highest award in computer science. And this is the paper that he published in 1961. And if you are interested, then you can refer this paper on Google. Right? Okay. Now, Quicksort is an example of divide and conquer problem. You can say algorithm. Right? So this is very, very important, very useful techniques to solve some problems. Like there are lots of problems comes under the divide and conquer problem, right? Like binary search, Quicksort, merge sort, and finding min max element in array, right? And finding power of an elements. These are the problems comes under the divide and conquer algorithm, and Quicksort is one of them. In this picture, you can understand that this is a bundle of a stick and it is a single stick. If I am giving you the bundle of a stick, that it is not an easy task to break this bundle of a stick. But if I am giving you the single stick, that is a small problem, then this stick can be easily break. Right. So this is the idea behind this one. This is a very important. Most of the problems comes under the divide and conquer. You have to break the big problem into the small problems, and so on. And those two sub problems also further divide into small ones, and so on. Right. This is for example, if you have a list of 100 names and you want to list them alphabetically, then you will make the two lists as A to L and M to Z. Right. A to Z is there, and you will divide this list into A to L. Let me write here A to L and what? 1 minute. Right. So suppose this is the name list, and you will divide the list of A to Z. Suppose this is A to Z, and you will divide this A to Z into A to L and M to Z. Right. The searching in A to L is easier than searching a particular name in A to Z. Similarly, you can break this big problem into sub-problems like A to L, what is A to F and G to L, right? Again, searching in a name in this range A to F is easier than this one, right? The basic idea is we are going to divide the big problem into sub-problems, and finally you will get a particular you can say particular character which you want to search, right? So this is simple idea. Now, actually, so in previous slide, we understand that Quicksort followed the divide and conquer approach. But actually, what we are going to do in Quicksort, let's discuss. In this Quicksort, we select a pivot element and reorder the given list in such a way that all elements smaller or equal than 8, all are one side, and those bigger than, suppose this is the pivot element. I am going to take this. Suppose I am going to choose a particular pivot element in a starting element of this array list, and after applying the partition algorithm, we find the proper position of this pivot, right? In such a way that all smaller are equal than n. All the smaller and equal than this one is one side, and all those bigger than this other side, right? So we will do this again in this sub list. We will choose one pivot element. For example, suppose I am choosing a pivot node name as P2, and after applying this partition algorithm before this one, we find that this is the proper position of this proper position. This is the proper index of this P2. From this P2, all the smaller element is in left side, and all the bigger element is larger element in right side. Similarly, we can do recursively, and at last we will find that all the elements will be sorted like this one. Right? This is the one of the simple example. Right? This is the array list. I am going to take this pivot element into 6 as a 6, and after applying the partition, we will apply all those things, right? Partition algorithm, and we will also execute the code also. We will apply the partition algorithm in this phase. We find that this 6 is positioned as here, right? And all the smaller element is in the left side, and all the larger element in the right side, right? Similarly, in this sublist, we are going to take a pivot node as a first node. You can take any node as a pivot node, but we will discuss later what is the problem in taking all these pivot elements. So this, I am taking the first element as a pivot node, and after applying the partition algorithm, we find that this pivot element is positioned here, and all the smallest element is comes under the left side, and bigger element in the right side. Similarly, we find that at the end we got all the sorted elements, right? One more thing, this Quicksort is also known as partition exchange algorithm, right? Why this partition exchange algorithm? Because we are going to, it's very clear, we are going to partition this array list, right? And what is the partition? This is partition. And what is the exchanging? In partition algorithm, we will see how this pivot element is exchanged from one element to another element, right? So there are two words are using in this algorithm, Quicksort. First one is partition. We are going to partition this one, and another one is we are going to exchange the pivot element with another element in such a way that we got a proper position of pivot element, pivot this node. Right. So that's why we are going to say this pivot partition exchange sort. Let's come to the algorithm of Quicksort. Right. So this is the array list. Right. This is the array list. In this array list, I am going to take this array name as array. For example, this array list is A, right? And this is P. First element is going to consider renamed as variable as P, and the last index is going to renamed as R, right? Now what we are going to do, we are going to apply P. This is a recursive code, right? And we are going to recursively call till P is less than R. Definitely P is less than R. P is less than R, right? So first we are going to apply the partition algorithm, right? So we are going to take this first node and we are going to apply the partition algorithm, right? Just ignore for a while partition algorithm. Just focus on this Quicksort, these two lines, line number 3 and line number 4. What this line number 3 and 4 says, Quicksort A, we are going to recursively call A PQ minus 1. What is actually this one? P. As we discussed earlier, this is the P is the starting index and this R is the last index. Right? And after applying the partition algorithm, we find that this pivot element is get the proper index value. Suppose this is a Q. This is the Q, right? And you tell me, now I am going to split this array list in two parts. So what should I write? This is the array, base address will be the same. Now tell me, this is the base, this is the first index P, and what should I write? This is Q, this is index is Q, then definitely this index will be what? Q minus 1. Very easy algorithm. This is P and this is Q minus 1. So that's why I am going to pass this recursive call Quicksort array name. Starting index is P and Q minus 1 is what? Just before the proper position pivot element. That is Q minus 1. So I am going to write it Q minus 1. And next is right side. Very easy also. Right side, what is the array? Array, the base address will be the same. This is a base array. And what is Q plus 1? If you know this is the index of this pivot element is Q, then definitely just before this Q, what should I write? Q plus 1. And what is the next? What is the last index? We have written R. In next recursive call, we will pass this array name Q plus 1 and R. Got the point? Again, this sublist is going again recursively calling going on, and this again, this will divide, this pivot element is going to divide in this such a manner that suppose this is the Q index. Again, this is Q minus 1 array P Q minus 1 array Q plus 1 and R. So this is a very easy recursive call. Now we will discuss actually what is actually partition algorithm. We will discuss. This is the actual partition algorithm, right? So in implementation part, I will show you what is how partition algorithm is going to work, right? So see, simple. Simply we are going to, this is a four line algorithm of Quicksort. First is partition. Partition is defined in this such a manner, such as way, and this is a Quicksort. This is the left side, this is the left side, and this is right side, right? And you know the time complexity of Quicksort is, we will analysis later, right? The partition algorithm is going to take order of n time, and left side Quicksort, left side partitioning is taking log n time. And you remember one thing, whenever array is going to divide into the half-half, you know the concept of half-half. In binary search, you also done half-half. Half-half means you are going to divide the array list into two parts. And whenever you are going to divide array list into two parts, half-half, then there is the concept of log n time complexity. Right. Right. So total is if partition algorithm is taking n order of n time, and this partition is going to log n time, half part, and this is also log n time, right? Log n plus log n is equal to finally log n, 2 log n, and order of n plus 2 log n is finally, you can say, order of, this is multiplication, order of n log n, right? Simple. This is the time complexity of this Quicksort. This is the best case, average case time complexity. But in worst case time complexity, order of Quicksort is order of n square. Okay? So we will discuss later at the time of analysis of Quicksort, right? But remember, in worst case time complexity, worst case order of n square, and average case and best case, the time complexity of Quicksort is order of n log n. Right? We have seen these two recursive code. This is Quicksort line number 3 and line number 4. Now I am going to apply this partition algorithm. How actually partition algorithm works, right? So now come to this one. Next, right? Is the array list index start from 0 to 9, right? this is the array contents. The name of this is array A, right? Okay. Now, actually, in this slide, I am going to explain partition algorithm. How a partition algorithm, how a pivot node, how an array is going to split actually, right? In this array list, I am going to take the first element as a pivot element. This is pivot element. But right now, I don't know what is the actual position of this pivot element, from where this array is going to split. For this, I am going to apply the partition algorithm, right? In partition algorithm, what should I do? I am going to compare this pivot element 3. I am going to compare this pivot element one by one from RHS to LHS, right? Okay. If any smaller element is found from RHS to LHS, then I will exchange this element, right? Let's see. 3. I am going to right to left. 6 is not smaller than 3, right? 9 is not smaller than 3. 4 is not smaller than 3. 5 is not smaller than 3. 2 is smaller than 3. In that case, I am going to exchange this element. So this should be 2 and this 3 should be here, right? The rest of elements should write like this: 8, 1, 8, 7, 8, right? 5, 4, 9, 6, right? Again, I am going to right to left, first step. In second step, I am going to left to right. All these things we will apply in programming also, and we will see the output also, right? Now, this is a pivot actually. This is a pivot, but again I am not getting any, right now I am not getting the fixed proper position of this pivot element, because in this left side there is this not a smaller element of this 3, right? We have to find the proper position of this pivot element. Now I am going to left to right. First right to left, then left to right. And from where you will compare one by one? From this one, right? Now I am going to compare this pivot element one by one from left to right, right? In such a way that any element greater than this element will be exchanged. The 0 is not greater than 3, okay? 1 is not greater than 3, okay? 8 is greater than 3. Now I am going to exchange this one, 3 to 8. 3 is this side, 3 this one, and 8 is this side, right? And rest of element I am going to write like this: 1, 3, 7, 5, 4, 9, 6. Okay. Now, first step right to left, again left to right, now again right to left, alternative, right? Now, this is pivot element, right now, but not proper positioned pivot element, right? Again, right? Now, come to this one, 3. Now come to right to left. But right to left, now we are going to compare this pivot element from right to left one by one in such a way that any smaller element will be exchanged with this element, right? So this is 3, 6. Now question is, from where should I move? Not 6, not 9. When is the recently updated? This is 8. Now you have to compare from this element. We are going to right to left, but from this element we have to compare. So now 8 is smaller than 3? No. 7 is smaller than 3? No. Okay. 3, it means we have reached at this position. It means there is no comparison, right? There is no comparison. Now we have to split in this case. We have to split this array in this case because there is no exchange, right? Now, what should I do? Now I am going to exchange this array into two parts, 2, 0, 1, right? And rest of element are 7, 8, 5, 4, 9, 6, right? And this is the actual pivot position of pivot element. Got my point? Now this is proper position of the pivot element, and now you can see all the elements in the left side it is smaller than this pivot element, and all the elements in the right side is greater than this element. This is the proper position. Now listen carefully. This operation is known as partition algorithm. Right. Now come to this one. Now come to the previous slide. Where is the? No. Okay. Where is this? Now come to this one. We have find this position of this pivot element, left side and right side. In this algorithm, we have to move this. This is partition algorithm. You are saying, right? Partition algorithm. We have applied partition algorithm. We have find the proper value of Q. Right? See, this is the value of Q. See, this is the value of Q, and this is ARR. You can again ARR. Right. Okay. If you write the algorithm again, if you want to write the algorithm, how can you write the algorithm of Quicksort? Just listen carefully. What is the algorithm? Pivot element. You find the proper position of this Quicksort as a partition algorithm using the partition algorithm. And what you have passed in this partition algorithm? Array name, array, and starting index is P, and last index is R. This is P. You can see this is P and this is R. Right? A, P, R I passed. Now Q is getting. Now come to this one. Next, what should I write? Quicksort. And what should I pass? Tell me. This is position of this 3, no? So 3. This is 2. So from this is array A, comma, what is this? This is P. This is P, and what should I write? Q minus 1. It's very easy. Q minus 1. Right? And what should I write in right side? Right recursive. Quicksort, array name, Q. This is Q, so this is Q plus 1. So this is Q plus 1, and what is the end? This is R. Simple. No? And this will work if what? If P is less than R. Right? And this is the recursive code. What is the recursive code of the Quicksort? And in this Quicksort, we have passed what? Array name and starting index and last index. Right? So simple. Now again this array list is going to divide into 2 parts. Now again I am going to take, let me change the color for the second pass. Suppose I am going to take this pivot element as a P, and now again I am going to write, I move right to left on comparing one by one element from right to left with this element, pivot element 2. Okay? So 1 is less than 2, right to left we have to check less element, smaller. First is smaller, remember this one. First is smaller element, right? And left right, first greater element. Right? So now I'm going to compare with 2. 1 is smaller than 2 first. Right? I'm going to exchange this one. So here will be 2, and here will, now let me change the color. This here will be 2, and this here will be 1, and 0 is as it is. Now this is pivot element. Now I'm going to move left to right. Right? So first greater element, 1 is greater than 2, no. 0 is greater than 2, no. Now this is the proper position of pivot element for this sub array. Right? So we have to stop here, and we have to split in 2, 1, 0, and there is no element. Right? Now you can see here this is a one sub list. Again I am going to call in recursive, assuming this pivot element first element and moving from right to left. 0 is smaller than 1, yes. So I am going to exchange this one. So this here will be 0, here will be 1. Right? Again I am going to move left to right, but this pivot is 1. 0 is greater than 1? No. And no more elements, this is going to split in two ways. This is 0 and this is 1. Right? Now you find that 0, 1, 2, 3 in sorted order. Right? Similarly, you can find like this one in this sublist also. Right? So let me find. I am going to take this pivot element as a 7 and going to compare one by one element from right hand side to RHS to LHS. Okay? RHS to LHS. Now this is 7 and looking for a smaller element. Right? So 6 is smaller than 7. Yes. So now I am going to compare exchange this one 6 and 7. Remaining element writing same as it is. Now what is this pivot element? Now I am going to move left to right, looking for greater element, right? So, but from where should I compare? This recently exchanged element is 6, so this one, from where? Again, so 6 is greater than 7? No. 8 is greater than 7? Yes. So I am going to swap this one, exchange like, so this will be 7 and this will be 8 and remaining element as it is. Right? Now I am going to move right to left. Right? Okay. Where is the pivot element? This 7. But now the question is from where we have to compare this one, from this 8. Right? Recently, where is the exchange now? Where is the 8 is this one and 7 is this one? You can write like this one, 8 and this is 7. Now here. Okay. So looking for a smaller element. 8 is smaller than 7? No. 9 is smaller than 7? No. 4 is smaller than 7? Yes. So I am going to exchange this one. 4 is this one, 7 is here. See, this is 5, 9 and 8. Right? Where is the pivot? This is pivot. Now the turn is turn of right to left. Right? Now, where is this exchanged? 7. This is the 7 and this is a 4. Now come to this. Now from where we have to compare? Recently exchanged position 4. From this 4 we have to move. Right? So this is 7 and looking for greater element. The 4 is greater than 7? No. 5 is greater than 7? No. Now we have stopped and there is no more element. It means this 7 is the proper position of pivot element 7. Now from here I am going to split this array into two parts, 9 and 8. Okay. Now in this subarray I am going to apply the recursive call, again applying the partition algorithm, this one partition algorithm, Quicksort left side and right side. Again similarly, again I am going to take this 6 as a pivot element and moving for first right to left, looking for smaller element. So 5 is smaller than 6? Yes. So I am going to exchange this one, 5. Right? So this 6 is going here, this 5 is going here. Now this is right hand side, RHS. Now come to the LHS to RHS. Now where is the pivot element? 6. Looking for greater element. Now 4 is this one. 5 is greater than 6? No. 4 is greater than 6? No. There is no more element. Now I am going to split here. 6 and this 6 and this is 5, 4. Right? Again this is the smaller list. Right? This is 5, 4. I am going to take the pivot element as a 5 and moving right to left, looking for a smaller element. Yes, 4 is smaller than 5. Yes, so I am going to exchange this 5 and this is 4. Right? This is now I am going to move left to right, looking for greater element. Greater element means 4 is greater than 5? No. So I am going to split this to 4 and 5. Right? You can observe here we have 0, 1, 2, 3, 4, 5 and this one is 6 splitted and 7. Now I am going to this sublist is remaining, applying a partition algorithm. Now this is pivot element. Right? Now I am going to move from right to left, looking for a smaller element. 8 is smaller than 9? Yes. So I am going to compare this one. Exchange this one. Now this is pivot element and moving left to right looking for greater element. 8 is greater than 9? No. And no more elements? It means we are going to split this one. 8 and 9. This is 8 and this is 9. Now you find that 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 is already sorted. Right? So this array list is sorted in this order. Applying partition algorithm and quicksort left and right. Right? Now come to this one. We have exchanged this one. This quicksort is also known as partition exchange sort. Right? So what we are doing? First thing is partition. We have done partition, right? And exchange them also. These are the exchanging. That's why this algorithm is also known as partition exchange sort algorithm. In the previous example, we have seen example based on the numerical numbers. But sometimes question will be asked like this based on characters, word. Like, so suppose I am going to take a word like quicksort example, right? So, see, this is the input quicksort example, right? So this is the input, right? But question, this is the input side, but question will be asked like this one. Suppose this is the KRATEL, this is the letters. You have to sort this letter in ascending order. Let's see. Suppose I am going to take this first element as a pivot element of this array list, and after applying the partition algorithm, we find the proper position of this pivot element, right? From where all the less element, smaller element comes into the left side, and all the greater element in right hand side, right? Okay, but how this k is going to come into the proper position, right? So let's discuss in next slide. See, this is the proper position of finding the position of k, right? So see, this is the k element, pivot element chosen is a k, right? I am moving forward right to left and looking for a smaller element, smaller than k. So you find that S is smaller than k? No. O is smaller than k? No. X is smaller than k? No. C is smaller than k. Now I am going to exchange this one, right? So k is going to exchange this C, right? C. So similarly, you find that this, after applying this exchange, you find that this is the k, this is the position of k, from where all the elements lesser element in left hand side and all the greater element in right hand side. This is the proper first pass to get the proper position of this pivot element, right? Okay, in next slide you find that this is the complete solution of this question. This is the quicksort. This is a given question, KRATEL. And now you have to apply the exchange partition algorithm. Now you find that in last ACEE, this is the sorted order of this array list, right? So we have done on numbers. You can practice on this such type of questions also. According to the research, the quicksort performance is optimal if the pivot selection to be middle of the array list, right? At the time of analysis of the quicksort, we generally use the middle of the array list as a pivot element, right? We will discuss later at the time of analysis, but right now what are the different implementation? First one is popular choice of pivot as the first element of the list is chosen when the input data is random. As we did earlier, we have choose first element of the list as a pivot element, right? Okay, another option you can choose as a pivot element, median of the array is a good option of choosing the pivot element. But problem is calculating the median will also take some time. Finally, the complexity of quicksort will be slowed down, right? So this is not a suggestible, but you can take the median of the array as a pivot element. Median of the array means you can take the index of the index after taking the medium of the array, right? The medium of the first three random chosen number is also selected as a pivot. These are already implemented. That's why I've taken this statement. Right? Above implementation considered as a simple Quicksort, right? But this is important. This already, according to the research, Quicksort performance is optimal if the pivot selection to be middle of the array list. That's very important. This will help you at the time of analysis, right? Because if you take the middle element of the array list, then definitely the array list will be split in half off, and the analysis of the recursive tree for the Quicksort is very effectively and easy to understand. Okay, now if the array is almost sorted, Quicksort will take longer than expected and perform slower speed algorithm. Definitely, this is the one of the disadvantage of using Quicksort, right? If the array is already sorted, and if you want to apply the Quicksort, then performance will be slower, right? To avoid this problem, what should I do? We can scramble before fed to the Quicksort. Okay, so thank you for watching this part. In next part, we are going to implement the Quicksort algorithm in C language.